Okay, let us slowly start. Thank you very much for coming in such a nice number to this wonderful place. It is a great pleasure to introduce Professor Ion Stojka. Ion is a professor at the UC Berkeley, where he holds Xu Bao Chancellor Chair in Computer Science. Well, it is EECS there. Ion has been one of the most influential computer scientists in the field of distributed systems. He has been instrumental in developing systems that have shaped how large-scale data processing, data analytics, AI workloads are built and deployed today. Some of his contributions include Apache Spark, Apache Mesos, SkyPilot, Ray. In my time, I was a PhD student where peer-to-peer networks were popular, so there he was with the distributed hash tables and a system called Chord. And most importantly also, all these amazing projects are open source projects. Now, Ion has also been a very successful entrepreneur. He has co-founded Databricks and Anyscale, both companies based on his open source projects. So we are delighted to welcome Ion here as our Strachey speaker, and please join me in welcoming him here. Thank you very much.
Thank you, Ivan, for such a kind introduction, and very happy to be here. So today I am going to talk about some research I've done over the past 10 years or so. And I have to start with a disclaimer. I know that you guys here are famous for theoretical computer science. I will only have one equation at some point in my slides. So this is very system-oriented talk. And let me start. So over the years, I've been involved in quite a few projects, some of them more successful than others. And in this talk, and these are two new ones, and in this talk, I'm going to talk about three projects which represent a slice through my work, Ray, vLLM, and Chatbot Arena, and they can be actually, can be composed into a mini stack, vLLM running on top of Ray and Chatbot Arena running on top of vLLM. So I'm going to talk about these projects, and the template I'm going to use for each project is this one. I'm going to talk about trends because in many cases, the trends is what shapes the research, the work I've done, challenges, the key ideas, what it is, tell you a little bit about the project and about the impact. So let me start. So Ray started in 2016, and the trends back then, which are still true today, is that AI demands are growing faster than single node capabilities, and the AI workloads also becoming more complex. So this is some more recent data about the growth in computation demands of training the top models versus time from 2010 to 2024. The Y scale is a log scale. And depending how you want different periods, you see that the demands have grown, computation demands have grown between 6.7 and 4.2x every year. So let's say it's 4x every year. At the same time, the node capabilities, and here we are talking about GPUs, if you look for the same precision, it's about 1.35x every year. And if you look about in terms of memory capacity, it's about 1.2x every year, and the memory bandwidth between the GPU compute and the memory, GPU memory, it's around the same thing, 1.2, 1.22. So if you put this together, what you see is that compute demands are growing 3 times every year faster than compute and memory capacities of, say, GPUs in this case, and of course, much faster than CPUs. A corollary here is that even if the demand stops growing today, in terms of, so you are not going to have larger and larger models. It will still take you maybe decades to still be able to train a model on one chip, which means that distributed computing, in particular heterogeneous distributed computing, is becoming more and more of a norm, right? That is an exception. The second point I made is that the AI workloads are becoming more complex. And let me start with this kind of old workload, and it's just a recommendation system. So what you do what you do in a recommendation system, you get the logs from the users, the interaction with the site. You do some featureization, you used to do some data preprocessing to extract the main features. Then you do some training to build the models to predict what recommendation to give you, like movie recommendation or things like that. You do fine tuning, so you have a new model, so you are going to play a little bit with different parameters of the model to see which parameters are going to give you the best results. And then you push that in production, and then you get logs, new logs, and then you try to improve the model to get better and better results. So this is what basically happened. And there are many more workloads. In 2015 and so forth, this was the emergence of reinforcement learning. If you remember, DeepMind, which was here playing Atari games, and then you have AlphaGo, then being applied to data centers, reducing the data center energy usage for cooling and many more. So these workloads again becomes more and complex. Recommendation system, reinforcement learning, then you have batch inference, and as of 1.5 years right now, it was a rise of test time computing and post-training. Okay, so the main challenge here is that when you want to build an end-to-end application, AI applications or ML application in the past, you have to put together all these components, right? To put them together. And you need to scale them, that we just discussed. The demands of the data processing and training these models is growing faster than capabilities of a single chip or a single node, okay? So you want to scale them. And at that time, and even today in big parts, you have distributed systems to scale each of these kind of stages, like data processing or preprocessing, training, tuning, and batch prediction, and so forth. So batch prediction, by the way, is basically before you in many cases, one of the use cases before you are going to deploy the model in production, you are going to test on the old logs to see how it performs before pushing it to production, okay? So in order to build your end-to-end pipeline, your end-to-end systems, you need to stitch together these components, right? And this is challenging for a bunch of reasons. First, it's hard to develop because each of these components becomes with its own API. It's hard then to deploy and manage because you need to manage these different distributed systems, and this system has its own semantics in terms of failures, recovery from failures, data consistency semantics, and things like that. It's hard to use resources efficiently is because typically you are going to have a cluster for each of these components. So it's hard to share the resources across components, right? So for instance, if you do training, you have a cluster for training, and then you have a cluster for inference. When you are done with the training, that cluster is hard to reuse for other things, okay? And finally, it's also slow because you need to move the data between these components. And the data, it's a lot of data. Typically, you write on the kind of blob store like S3 or something like that, and you have to read it. So it has a lot of overhead, reading, writing, serialization, deserialization, okay? So what Ray provided is one system which is general enough to support all these workloads, okay? So this is Ray and has a component that you see at the bottom is we call it Ray Core, and it's a unified computing framework for distributed applications. And then you have on top of it a bunch of libraries running on Ray Core to support these different workloads. But now you have a system which is going to, you can use system for your entire end-to-end application, Okay? So that's basically what it is. So what is key idea? So what behind Ray? So Ray, what it does is that it takes a procedural language like Python and generalize it to a distributed setting. That's basically what it is. And it focuses on flexibility by exposing the parallels to the developers, right? So the developers can build application with various patterns of parallelism, like nested parallelism and things like that. And one of the questions it's always been asked is that why not a declarative language? You just a language what to do, and the backend, the compiler or whatever, is going to decide how to do it, right? I think there are a few challenges with that. First of all, there is no popular general purpose declarative language, which, and I've been working with Datalog and other languages, so I've been doing a little bit of work on that. And, you know, adopting a new language is hard, let's face the truth. And we didn't want to invent one because of these reasons. And at the same time, when we started the work on Ray, Python was emerging the lingua franca for AI. So all AI people knew Python, and all the libraries like TensorFlow, PyTorch, they were libraries within Python. Okay? So what kind of, there are, these kind of procedural languages, there are a few concepts. Actually, there are more, but these are the ones which are relevant for Ray. First of all, you have, in terms of the compute, it's like you have function and classes, right? Classes are stateful operators, right? And function in general, if they shouldn't have side effects, so they are stateless operators. And then you have concurrency, obviously, and this is some form provided by Python with async IO API, which allows to execute things in parallel or overlap, for instance, computation and communication and other things. And the other one, which is kind of very more low level, but it's important, is that passing, especially for large amount of data, is the ability to pass the data by reference, right? Instead of by value, right? Far more efficient when you have large amounts of data, okay? So these are the things we kind of try to capture in Ray. And we encapsulate this in this fast compute model, is what we call it. And so again, you are going to take classes and functions and provide ability to instantiate transparently these function and classes remotely as tasks and actors, right? You've seen a lot of actor languages. Then we have a shared in-memory distributed objects, which enable these passing arguments by reference. And then we have these features, in particular distributed features, which are references to objects, to arguments, as well as the results. And in some cases, these are to the results which are created by tasks or actors even before being scheduling. So they are exist abstract level. You don't know even where the object is going to be created. And this obviously it enables concurrency and concurrent execution and parallelism. The Ray core has a very minimal API. These are all the functions, the main functions, the core functions. And I'm not going to read all of them. I'm going to demonstrate a few of them with a few examples. So here is a very trivial example. So say you have a function which is computing for 1 second and return a result. And if you execute that in traditional Python, I'm not talking about multiprocessing Python, you call this function twice, it's going to take you 2 seconds to run, right? Because it's sequential, right? Now, what Ray is doing, you are going to have to use this kind of decorator, ray.remote, and it's doing under the hood when you are going to call this, you are going to call f.remote, then it's going to take that function, so here when we execute that, and it's going to submit a task for that function, which will be scheduled by Ray somewhere in the system, can be on a different worker, on a different node. This function is not blocking, okay? So it's going to return immediately, and it's going to return a reference, a future, to the result, okay? Because it's not blocking, you can execute now the next call to the function f.remote. and is going again to get you back a reference to the result. And finally, you do array get to get the results. Now, this is blocking function. And under the hood, Ray submitted these tasks to a local scheduler, and the local scheduler will figure out where to schedule these tasks for each of the functions. And then they are going to be scheduled, executed, in this case in parallel because there is no data dependency, and you are going to get the results. And because these two tasks are executed in parallel, you are going to, now the entire program is going to take only 1 second. Okay? So this is functions. You also have classes are instantiated as actors. Again, you do that, you just need to say array.remote, and then .remote when you instantiate the class and when you call the method of the class. By the way, this .remote, it's actually not needed. The reason we preserve it in the language is to make the developer, the programmer, aware that this is going to be, can be executed remotely on a different machine and can be slower. But also just to give an extra hint to the developers. It also has the ability, Ray, to, which was early on, we made this decision, to specify, the programmer can specify resource demands for a particular function or of a particular class when it's going to be instantiated in terms of number of CPUs, GPUs, memory requirements, and things like that. Okay? This is class task and actors. Then I mentioned you have a shared in-memory object store. So this is shared memory. It's read, it's write only, read and read. So you don't update. It doesn't provide the ability to update data, and this makes obviously keeping the consistency much easier. Of course, at the programming level, you are going to update it, but under the hood, you are just going to create a new version, a new version of the data with modified data. Okay. So, and here is another simple example where you have two functions where f and g, you call f, and then you pass the result from f to g. Okay? So again, this what happens here is when you are going to call f.remote, it's unblocking call. You are going to execute. Eventually, Ray is going to instantiate the task associated with f and return the reference to the result of f, this distributed future, and that is going to be passed to G, right? And G.remote is going to, the Ray is going to instantiate the task for G, maybe on another worker, on another node, and return the reference, distributed future, for G, and then you can get the results. So now you have a dependency between f and g, the data dependency. Ray knows that, and basically is going, before executing g, it waits for the reference to be resolved, which means that f should finish and produce a result, in this case x, and then now that x is available, Ray will transfer x to the node which runs g, and now you are going to finally run g. The main point here is that in this particular case, x is transferred only once between node 1 and node 2, which runs f and g respectively. And the reason I'm giving this example because we have to if you want to contrast with remote procedure call, right? The remote procedure call is again a way to run function remotely, and you have that in many languages and so forth. But in most of the remote procedure calls implementation, the data, the arguments are passed by value, right? And in this particular case, for instance, you have to execute x, then you are going to get the value back, You need to execute f, which will get the value back x, just to pass it to g, okay? And then g will be executed on this node 2. And in this particular case, as you can see, you have 2 transfers of x in the system instead of 1. But this, again, you knew that, right? I mean, that's was the advantage of using references, passing the argument by references to avoid extra copies. And that's true for the single node. And it's also true, obviously, for a distributed system. Okay? Now, I will also try to mention some ongoing work, and obviously a lot of ongoing work. It's about improving the GPUs. What we are witnessing today, we have been already moved from a CPU-dominated compute infrastructure to a GPU or accelerator-dominated infrastructure. And we do a lot of work on direct to reduce the overhead for direct GPU to GPU communications, and implementing different collective operations and so forth. This is one example. Basically, direct GPU to GPU communications is like in the original array, remember we have this kind of object store. So object store is implemented in the CPU memory. So what happens if we want to transfer some data from one GPU to another, like a tensor? What happens is that this tensor is moved from the GPU memory to the local RAM memory of the node, then going to go through the object store to the RAM of the receiver, and then from the CPU memory of the receiver to be transferred in the GPU memory. So it's kind of quite slow, right? And obviously what we want, and there are a lot of copies, a lot of RPC calls. So what we want, obviously, it's direct GPU to GPU communication. And memory statically allocated and everything for optimizing it. So one thing I wanted, I give you this figure because initially when we did that, and this is still experimental, we thought everyone will use direct transfer between GPU and GPU 0 and GPU 1. But there is one instance, to our surprise, in which people preferred the one is coming on your left to go with the old traditional way of transferring the data through the CPU memory. Do you know why? Do you know what is that? What is a case in which you may still prefer the slow transfer over the right one? It turns out that when you do GPU to GPU transfer, it's a synchronous operation, okay? You need also to synchronize the sender and the receiver, so you need to allocate the memory in the GPU receiver to be ready to receive the data from the sender, okay? Now, in this case, it's more asynchronous. You need only to be ready to allocate the GPU, to be ready to get it, to allocate the GPU memory when you have the tensor here on already it's instantiated the tensor on the local machine in the CPU memory. So the amount of time for which you keep the GPU memory allocated to get the tensor is going to be higher when you have direct GPU to GPU communication than when you have through memory, right? Again, because it's synchronous. So if your GPU memory is extremely the premium and is a bottleneck, you may prefer the left-hand side, okay? So there are many, like I mentioned to you, Ray is very flexible. It also provides support for heterogeneous infrastructures. And here you have, batch inference where you read data, you preprocess the data, you do some inference, and you write the data. And here the data preprocessing and post-processing can run on CPUs, while the inference can run on GPUs. And by doing so, you can save a lot of cost instead of running everything on GPUs. And there are many workloads you can support here, multi-node search and so forth, fine-tuning, embedding computation. Ray is also emerging as a standard, not standard, but the framework of choice for post-training. There are a lot of post-training frameworks being developed over the past year, many of them using Ray and also using vLLM or SGLang, which are systems we also developed at Berkeley. Okay? So Impact has been a very popular framework. Actually, it was used by OpenAI in their training infrastructures to train ChatGPT, GPT-4, and others, and by many other companies to build their AI infrastructure. Very fast growth, especially in the past year. This is a number of downloads, and this is GitHub stars compared with other distributed frameworks, popular distributed frameworks. So as you can see, the growth is accelerating. So this was Ray. I have two other projects I'll have to finish quickly. The next is vLLM. Okay, so vLLM is about inference. And what kind of change? So what kind of the trend? So the trend obviously was the large language model. So what was different about this model from the point of view of training and inference? It used to be that in the traditional machine learning, for every task, for every use case, you are going to train a model, and then you are going to serve the model. So train, serve. Large language models are much more general, and they are kind of provided to do multiple tasks. So you train a large language model, and then you can use it for multiple tasks. You train once, and you do the inference for many, many tasks, okay? So that means that the inference actually becomes even more important. And you have a lot of, this was happening, by the way, in 2023. This is when we started the research. At that time, it was very expensive to serve these models, okay? So you can have, if you remember, Egypt, you can only serve a handful of requests per second. That was A100, if you remember, for those of you. That was the top GPU in 2023, okay? And so you have neither, the cost per request was very high. And why is that? Everyone knows that, so I'm going to go quickly. Is because, as you know, these models are autoregressive models, and when they generate a token, they generate a new token based on all the previous tokens. Okay? So you have this kind of strong dependencies, this attention mechanism. Okay? And so generating one token at a time, because you have the dependency, it doesn't exploit the GPU parallelism, right? The GPUs are fast and have a high, compute capabilities, but they do that when you can exploit their parallelism, right? But now you cannot exploit them because of these dependencies for one request. So of course, if you cannot exploit for one request, then what is the solution? Well, I'm going to try to serve multiple requests at the same time, right? So you request a batch, you are going to process a batch of requests. The problem is that now you are going to get out of memory, so the memory becomes a bottleneck. So why is that? Well, because again, of this dependency, to generate the next token, you need to store in memory, and this is how memory is organized. You have the number of, this was as 40 gigabytes at that time, 30 bytes, 30 billions LLM, that was Llama model. So the precision at that time was 2 bytes. So you have 26 gigabytes, which was 65% of the entire GPU memory. And then you have this other is activation, a few percent, and then a KV cache. So KV cache, where you keep the data, temporal data to generate the next token. So in this KV cache, you need to keep the embeddings, for the entire prefix, right, for each request, right? And each token, which embedding, it was like 1 megabyte. So one request can have several gigabytes, okay? So that's a problem, okay? So, and when we looked, actually, this was compounded by the fact that before, what happens with the memory was contiguously allocated. That's the easiest way to allocate memory, contiguously allocate all the memory you are going to need, right? And you also need to, because it's contiguous, you need to provide space for the future future tokens, okay? Of course, you took systems 101, you know that lists that can lead to contiguous memory allocation can lead to fragmentations. And you can lead to internal fragmentation because I'm going to allocate a space for a request, but I don't know eventually the length of the output, right? And because I don't know, I'm going to have to probably allocate more than I should. So you have fragmentations there. You also have, this is an interesting one. So the interesting one is the following. So let's say that you know exactly how long is the output, okay? So then I can allocate a block of memory to fit all the output and no more. Well, it turns out that even this is not optimal. So why is not optimal? Say I have to allocate 1,000 tokens for output. Now, these tokens are going to be filled sequentially one by one, right? So initially, I have 1,000 tokens free. Next token, I'm going to generate 1 token used, 999 free, and so forth. So during the process, dynamically, I'm going to waste a lot of tokens which are allocated, space which are allocated in the future, right, which are not used. They are going to be used eventually, but for a long time, they are not going to be used. So this is kind of reserve instance and external fragmentation. I'm going to not talk much about that. And this was at that stage, this was how the memory was used. And the only thing you need to look at here, it's about the green part. These are, the other color are different kind of fragmentations, but this is an effective memory which was used by the inference systems at that time. The most of it, the largest one is 38%, but 38% you have this kind of oracle is saying here. Oracle is what I told you. Assuming that you know the future, which you know the future, how long is the request, still you are going to effectively use only 38% of the memory. If you don't know the future, the best at that time was 26.8%. The rest was kind of wasted. So, as you know, what is a solution? You still have fragmentations and things like that, challenges. Segments, if you remember, in operating system, what do you do there? Paging, you have this kind of pages which are fixed sizes, a few kilobytes and so forth. And then there is no fragmentation, external fragmentation between these pages. And then you still provide to the application the illusion of a nice address space, which is contiguous. But this address space is going to be mapped to different pages under the hood, right? This is exactly what happens here, right? So this is what memory management. You have the process A, process B. They have their virtual memory, which is mapped, which is contiguous for each of them, the virtual memory. And this virtual memory under the hood is mapped to these pages, which are all over the place in the physical memory. So the same we are going to do here. And this is logical KV block, so everything is contiguous, each block after another. But in the physical memory, you are going to have different blocks are going to be spent at different location. A block consists of multiple, it's a fixed size, and consists of of several embedding tokens. In this case, 4, right? 4 tokens. Okay. So then how do you go from the logical to the virtual block space? Well, you have a mapping. You have a table which index each logical block to a physical block in memory. And then you have another field, which is a field here, which basically says how much of that block has been filled with tokens. Okay? So in this case, the block 1 is 2, and now you are going to generate the next token, in this case, and you are going to put in the corresponding block in the physical memory, and so forth. Now, when it is full, the block, they are allocating another block in the physical memory, right? So it's kind of simple, and again, what need. This allows also, if you are having multiple, requests and so forth, and answer with the same prefix, to share the prefix more efficiently. You can do parallel sampling, multi-turn, when you have multi-turn conversation and things like that, okay? Now, let me tell you, because it's interesting, it's very much like paging in kind of virtual memory and operating system, but there are also a few differences. So similarities, pages are very similar with, KB blocks are very similar with pages, and you can share pages across processes, things like if you have common prefixes for the request, or if you have system prompt. The system prompt is used for every prompt, right? So it can be shared across all prompts from all the requests. But there are some differences, okay? So when you talk about evictions, you see, and when you evict, when you run out of physical space or memory space, what do? You evict pages, right? To make room to bring a new page you need, right? And that page typically is stored on in a swap space on the disk, and then you can bring it back later. So on a slower storage, but bigger storage. So in this case, there are two differences. You see, because the dependency, when you need to generate the next token, you need all the tokens before that, okay? So it doesn't make sense to just page out one block, right? You have to page them all of them, right? Okay? Because you still need to do all of them when you are going to get the next token, right? So you need to do you can do request level eviction versus page level eviction, which will free more memory for other requests. The other one also is interesting. It's like you do, like I said, in the operating system, you do page in, page out, and page in. You store the page on a disk, on the disk. But here, because because the GPUs have so much compute, sometimes it's more efficient to throw away the block and to recompute, to rematerialize it when you need it. Because recomputation is faster than just storing it for, in this case, can be on the CPU memory and bringing it back, okay? This is some of these differences. So what was the result? The result, we got 96% in terms of the memory utilization at that time, and this converts directly in the throughput, right? So 96% compared with 26.8%, it's almost 4 times higher throughput, because you can fit now in a batch and you can process at the same time 4 times more requests, okay? It's also actually, this is one of the fastest growing projects I've seen. I was part of it. That's kind of GitHub stars, the vLLM. SGLang, it's another, unfortunately, I don't have time to go over it. It's another project we developed in the lab. It was a top open source project on GitHub in 2025. And I also wanted to show this, how hard things are in practice. And this is about, like what is saying this is that the number of models which are supported actually September last year by vLLM, and the number of accelerators it supports. It's over 260 accelerators, and I don't know, it's like 500 model architectures. It's very, very complicated, very complex. Okay, so yeah, and it's used. And what I want to say here is that this page attention is actually, as a techniques, vLLM is the artifact, but page attention is used now by all these inference systems, not only vLLM in the industry. So it's nice to see that. So the final one, and it will take me 10 minutes of this as well. So it's LMArena, rethinking the LLM evaluation. So this is a different one, and this is hopefully, it's like I thought it's a nice story, and it's the end of the talk, so hopefully it's going to be more engaging. So look, this is Dave Patterson, Turing Award winner, and he has this famous quote, "For better or worse, benchmarks shape a field," right? And this is absolutely true about AI. You have all this kind of ImageNet and CIFAR and all of these early benchmarks, and you have more and more now benchmarks, right, to compare and to see which models are better. So here our story. So when at the time when Meta was opening source their models, they open source Llama in 2023 in February. A group of students then took that model and took this kind of shared GPT data, which was shared GPT was a data, the prompts and the results that people were sharing over the web, and use that to fine-tune, right, to further train this Llama model and call the model Vicuña, okay? And this was high-quality data, shared GPT, because people only shared the prompts and the results they were, excited, they were proud about, okay? So now, and we offered, so the trend here is the rise of chatbots, because you offer Vicuña via chatbot interface. That was a chat GPT early days. And the question is about how you are going to evaluate it. You have this kind of benchmark, with a static benchmark, the time MMLU, HELM, and so forth, but they are static. Static means they are also prone to contamination. By contamination, what I mean is that the models, this large language model, as you know, are trained on all the data which is available in the internet, and these benchmarks are available in the internet. They are going to be trained on this benchmark, and then they are going to be evaluated on the same benchmarks. And then do not capture human preferences, right? It's not only about correctness, it's about the style and so forth, right? So that's kind of the problem. Okay, so how do you do it? Now, this is a contamination. It's an example to show you that it's real. This was ChatGPT is some kind of, this is kind of some message, I think was X or on Twitter. So code force, right? It turns out that it was 10 out of 10 solving correctly, before 2021, and 0 out of 10 after that. And that was incidentally the cutoff date for data used to train GPT, right? Of course, you are trained on the solutions. You are going, hopefully, to remember all these solutions. So that was the real problem. So you need human evaluation. So what do you do? What do you do as a faculty, right? Like, okay, so you get some students, right? Give them some pizza and say, okay, ask, and these are the prompts from different models. See which is better, okay? Soon we realize that it doesn't really scale, okay? And why it doesn't scale? Because the answers and the evaluations take time, are not obvious. It's not like a math problem, this is good and right. And here are two examples. One says this question, is develop a Python program that reads all the text files under a directory and returns top 5 words with the most number of occurrences. Okay? So everyone can do that. And I'm not going to ask you to program, it's not a question, but I'm going to give you 2 solutions provided by 2 large language models, 2 chatbots. And I'm going to ask you which one is better. How many of you think it's A, assistant A? Assistant, right? What about assistant B? Okay, I know that Oxford is very strong on all the other departments. So here it's a biology. Photosynthesis is a vital process for life on Earth. Could you outline the 2 main stages of photosynthesis, including where they take place within the chloroplast and the primary inputs and output for each stage? Again, I'm not going to ask you which are of those. I'm going to give you 2 answers. And I'm going to ask you which one is better. A or B? How many A? B? Okay. Good. So now we have a challenge to our, in our hands, how we are going to scale this, right? It turns out like what we did is well, GPT-4 was released 2 weeks before, right? And they said, well, why don't, students are very inventive, say, why don't we use this GPT-4 to be the judge, right? Say, okay, you tell the GPT, this is a question, these are the answers. tells me what is the best one and the answer. Or it was a question, it was graded from 1 to 10 or something like that. Okay? And that was this is LLM as a judge, right? This is, and the paper about that and things like that. So this is, I think that this was the first use of LLM as a judge in the open. I think that Microsoft did when they did the internal evaluation of GPT. They have a very strong relationship at that time with OpenAI, but this is the first application in the open. Okay, and we apply it, and for instance, like for this first question, the Python question, it turns out that assistant A didn't handle case sensitivity, punctuation, and so forth. So in this case, B was better. And in this case, while A looks much more comprehensive and detailed, actually again B is better because A confuses which are the inputs and outputs from the two stages. Okay? So when you look about this explanation, now it's much easier, right? It's like to do it. Okay? But we did that, but people come back to us and say, hey, yeah, LLM as a judge again, it was very early on. It sounds good on these data points, but really, how does it perform? So you're back in square one to have human evaluation to compare, right? And again, how to scale it. So human evaluation, ideally you have for every questions, you want to rank the LLMs. I have one question, I have the answer from 10 LLMs, rank them, right? And then you do what is the better. Now, we know that ranking n choices is hard, and easier is to pick the best out of n, right? But even that is hard. We know this paradox of choice. So the easier thing, you have to pick best of two. You cannot do less than that. And it's the least you can do. So that kind of was one angle. Okay, so pick best answer between two LLMs. And now there are many ways you can do it. One, you organize a tournament, right? Each LLM with each LLM for each questions and so forth. The problem with this, it doesn't scale. It doesn't scale for many reasons. One, it's because you have to play 10 square, right? To play everyone with everyone. But the other one, the bigger problem is that it's static, right? You cannot enter new steam into competition, right? Unless it ends. And these LLMs are starting to, new LLMs are being released, every month, every week then, okay? But fortunately, there is another way to do it, and this is our key idea too here, is that ELO-like rating, right? Like chess. And there are many other similar ratings in other sports. Almost every sport has one, in which you can have a meaningful rating with players not playing everyone with everyone, and it's more related about with the strength of the opponent, right? If you are going to beat a strong opponent, you are going to get a bigger bump. If you are going to beat a weaker opponent, you may get very little bump, okay? So that's basically what it is. So this is what we developed. This is kind of Chatbot Arena. So what we did, we provided this kind of interface. People come, we provided these models for free. You ask questions, you get two answers. So this is, very early days. So the question is very simplistic. The answers are also simplistic. And then people can say A is better, B is better, is tie, or both are bad. And then you compute, we use Bradley-Terry model to compute rating, this arena rating. And we rank these models with the proper confidence intervals and things like that. Okay, so that's what I've done. Okay, there are many categories here you can rank these models. We add a lot of, let me just, okay. Now you have user evaluation and you have LLM as a judge, right? So now you can do a proper study. So you wrote this kind of paper, which actually this was in the same paper, like LLM as a judge. And what we did, the findings are that the LLMs are biased when they do make judgment, very much like humans. You have, for instance, position bias. they prefer the first answer. If you give them question, answer 1, answer 2, they prefer the first one. Verbosity bias, sometimes they prefer longer answers. Self-enhancement bias, they certainly prefer answer from itself, okay? Or the other LLM in the same family. And at the same time, they have limited reasoning capabilities. They are not good at math, okay? And then we look about the agreement between two humans, right, experts, and also between humans and large language models. And, at the end of the day, it was quite similar. The human-to-human preference was 81%, and the human-to-GPT question was 85%, okay? So that's kind of, okay. We have many other modalities. This is one question I asked last night. Please show an image of the Oxford University at 4 p.m. in February. Okay, it's very, very close to that. I selected A being better. And yeah, this is, again, on many modalities. What can you do with the data? I'm going to be very quick here. And let me just show. So here is one idea, is that prompt to leaderboard. So what we do here, and we develop a model that's kind of, I think this is you can look at this equation and I'm telling you what is here. So what we do here, you have a prompt. If I have a prompt, I can generate, on the fly, a rating for different models for that prompt. So how do you do that? Maybe we never seen that prompt. However, I've seen a lot of prompts similar to that prompt. So you use votes to these other prompts which are similar to the new prompt as a proxy to compute the leaderboard for that particular prompt. And it has many applications. You can, given a cost target, you can maximize the ARENA score, or given an ARENA score, you can minimize the cost, right? And this is different models at that time when I wrote the paper. And with this one, for the same cost, you can get 30 more ELO points, better models. And for the same accuracy, ARENA score, you can get 2x cheaper by using this prompt to leaderboard and picking the right model, okay? It's like it has it was very rewarding because right now it's like most foundation labs, before they release a model, they evaluate these models also on Chatbot Arena. Now it's called Arena, okay? And we have a lot of users, votes, and things like that. Yeah, these are some people tweeting when the new results come out. Okay, so I'm going to go very briefly. I'm going to have these 3 slides, and then I'm going to go to conclusions. So what are the lessons we learned? I think these are important. I don't want to skip on this. Lesson number 1 is that trends do matter, right? With the emergence of complex AI workloads and heterogeneous distributed systems was really important. With vLLMs, the autoaggressive nature of LLMs, so it's a problem changes. The problem changes. In most of the cases, the solution is going to change, right? And so chatbots, LLMs, like autoaggressive natural LLMs and complex AI workloads is what actually determine us to work on these systems, and actually they are the drivers also behind probably their impact. Lesson 2, the simple solution matters, obviously. The Ray, you see, it has the Ray Core minimalist API. vLLM, the page attention is quite simple. LLM as a judge and head-to-head evaluation using ELO-like ratings, very simple ideas, maybe too obvious in retrospect. And the reason this matters is that it's easier to understand also by other people, right? And apply them. Like I told you, page attention is used now by everyone. And also ELO-like rating, you see a lot of other people doing it, or LLM as a judge. And this is related with the impact, because if you understand something, how it's working and how to do it, it's much more likely you are going to do it, right? Versus something which is hard to understand. And the other one I want to say it, it's like, you have to plan for flexibility and rewriting when you develop this kind of systems, because you do not have the all requirements. The requirements evolves as you are going to develop these systems. With Ray, we rewrote the Ray 4 times. With vLLM, we already rewrote it once, and it's 2.5-year-old project, and now it's another rewrite, and so forth. So I'm going to skip over the next one, and I'm going to move to questions. So summary is that I do believe in open source. Everything we've done at Berkeley, it's open source. We actually don't, in the lab I am, in my lab, we don't file for any patents. So everything is for public consumption. And I talked today about these 3 of these projects, Ray, vLLM, and Chatbot Arena. And I do believe that we are just scratching the surface, and there will be many, many more challenges we are going to have to address. And I hope that most of them will be addressed in open source using open source technologies. Thank you.